This is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in previous session, already we have started the solid mechanics and material subject. In this, already we have learned simple stresses and strains and types of stresses and how to calculate the stress and what is the relation between the elastic constants we have studied. But in this session, so I want to explain about stress strain diagram. So this stress strain diagram is very important in solid mechanics. So in this session, what are the importance of stress strain and then what are the important points involved in this stress strain diagram, we will see. So the course outcomes are at the end of the course, the students should be able to explain the concepts of stress strain. So already have studied, we have seen in a previous session. So material constitutional relationship and strain energy induced in linear, elastic, homogeneous and isotropic materials subjected to forces. So this is the CO1. So now, so according to the CO1, we will discuss all topics and then at the end of the course, the students can able to explain whatever discussed in session. So they can able to answer. So first of all, before going to enter stress strain diagram, so these two properties are very important, the elasticity and plasticity. So these two are, the elasticity and plasticity are properties of the material. So these two are fundamental concepts in the field of material science which describe how materials respond to external forces. Suppose when a material is subjected to some external force, so the material, how this material respond to the external force. So it may be deformed, it may be break, so it does not change any shape. So that is based on, that it depends upon the property, the nature of the material. So the elasticity refers to a material's ability to return to its original shape and size after the external forces or stresses causing deformation are removed. So simply this property is the material able to regain its original shape after removal of load. So apply load up to certain limit and then whenever you remove the load, again regain its original shape. So due to its elasticity property. So this phenomenon is known as elasticity. So can you give example for this one? The example you can say for a rubber. A common example is a rubber band. So the rubber band is the example for this elasticity property. When you stretch it, it deforms, but once you release it, it returns to its original shape. So according to the elasticity property, in this type of deformation, the material will deform when stress is applied, but will return to its original form once the stress is removed. This behavior is reversible. So whenever the load is removed, they return to its original form after removal of stress. So this is called as a reversible behavior. So example, rubber band. So one more example is spring. Suppose one spring is connected to mass. So whenever remove, so always acting downwards, whenever remove this mass, so regain its original shape without mass. This type of phenomena is known as elasticity. So what about plasticity? So plasticity opposite to the elasticity property. So first I will explain the Hooke's law and then we will see the plasticity. This law, according to this law, the stress is directly proportional to strain in the elastic region of a material. So it means this law describes the linear relationship between stress and strain. It states that the strain in a material is directly proportional to the applied stress. So provided the stress does not exceed the material's elastic limit. So here the stress is directly proportional to strain. So the Hooke's law states relationship between these two within the elastic region of the material. So we can write sigma is equal to E epsilon. So the elastic limit E, the elastic limit Young's modulus or modulus of elasticity E is equal to sigma upon strain. So it gives Hooke's law. So directly proportional to the applied stress. Now come to this plasticity property. So plasticity refers to a material's ability to undergo permanent deformation under applied stress. Once a material has been deformed plastically, it does not return to its original shape, even when the applied stress is removed. In the case of elasticity, whenever remove the material, it regains its original shape. But in this case, the plasticity, the material has been deformed plastically. So whatever deformed is occupied permanent shape. So does not go back. So this is irreversible deformation. So when the stress exceeds the material's elastic limit, that is yield strength, the material deforms permanently. So this is called as plastic deformation. So the plasticity is opposite to the elasticity property. So these two properties plays important role in solid mechanics. So the mechanical properties and the material properties are very important before designing a component. So example for this plasticity, a piece of modeling clay and the modeling clay, when you shape it, it remains in the new shape even after you stop applying force. So even you are remove the load, it remains. So whatever occupied the new shape, it remains in the new shape only. The yield point is the stress level at which a material begins to deform plastically. Beyond this point, the material will not return to its original shape. So this phenomenon is called as plasticity. Now, I will explain stress strain diagram. What is this diagram? So, in designing various parts of a machine, it is necessary to know how the material will function in service. For this, certain characteristics or properties of the material should be known. So, the mechanical properties mostly used in mechanical engineering practice are commonly determined from a standard tensile stress. So, in designing of various components, in mechanical engineering, if you want to design any component, you should know the properties of the material. So, what will happen in a service if you apply load? How it will react? How it will function? For this, certain characteristics or properties of the material every designer should be known. So mostly the mechanical engineering, the mechanical properties mostly used. Those mechanical engineering, the practices are commonly determined from a standard tensile test. So it is determined some properties from a standard tensile test. What is this tensile test? So this test consists of gradually loading a standard specimen of a material and noting the corresponding values of load and elongation until the specimen fracture. So it consists of gradually loading a standard specimen. So take the standard specimen. So the standard specimen, so you can take this standard specimen. So under this, this is total length, and you can gauge length. So noting the load is applied and measured by testing machine. The stress is determined by dividing the load values by the original cross-section area of the specimen. So here original cross-section area, load upon area. So it gives you will get stress value. So gradually loading a standard specimen material and noting the corresponding values of load and elongation. So what is the load and elongation? Suppose I apply 10 newtons. What is the elongation? So 20 newtons. What is the elongation? So 30 newtons. What is the elongation? Note down. Until the specimen fracture. So how it will react according to the load? We will observe by using this tensile test specimen. So the load is applied and measured by testing machine. The stress is determined by dividing the load values by the original cross-sectional area of the specimen. The elongation is measured by determining the amounts. The two reference points on the specimen are moved apart by the action of the machine. So two reference points, from one point reference and the second point this one. So this is the original distance between the two reference points is known as gauge length. So the strain is determined by dividing the elongation values by the gauge length. The values of the stress and the corresponding strain are used to draw the stress strain diagram of the material test. So the values of stress and the corresponding strain are used to draw the stress strain diagram. To draw all values of stress on a y-axis and strain in x-axis. So of the material tested. A stress strain diagram for a mild steel and a tensile stress is shown in this figure. The next slide I will draw. So I will explain. So what is this stress strain diagram of points, important points. All points we will discuss. So that is the basic idea of the stress strain diagram. So this all points determined by the testing of standard specimen under a universal testing mission UTM. And so noted these values on a graph paper, on a graph sheet, and x-axis and y-axis, you will get the stress strain diagram. So by using this diagram, you can calculate what is the percentage in elongation, what is the percentage in change in area, you can calculate. See, first we will draw the stress strain diagram. So from this x-axis and y-axis, stress values and strain values. Stress and strain value. First you draw one line and mark a point A. So 0 to A. So that is starting point, initial point, you can say origin O. And then so next B and C and D and E, and the last point is F. E point and F point. So now what is this origin to A point, and then B and C and D and E and F we will discuss one by one. So first the proportional limit. We see from the diagram that from point O to A is a straight line. So the O to A is straight line. So this is proportional limit. Proportional limit. So which represents that the stress is proportional to strain. Here, the stress is proportional to strain. Beyond point A, the curve slightly deviates from the straight line. So it is thus obvious that Hooke's law holds good up to point A, and it is known as proportional limit. It is defined as that stress at which the stress strain curve begins to deviate from the straight line. It is defined as that stress at which the stress strain curve begins to deviate from the straight line. So here up to here straight line 0 to O to A. So this line, whenever the straight line, this straight line curve begins to deviate from the straight line. Here from straight line to B, here started deviated from straight line to some curve up to B is called as elastic limit. So it may be noted that even if the load is increased beyond point A up to the point B, so up to here the proportional limit, here proportional limit. Proportional limit. But 0 to here, whenever this this O to A, the curve deviates from the straight line. That is elastic limit. Elastic limit. So, the material will regain its shape and size when the load is removed. So, this means that the material has elastic properties up to the point B. So, this point is known as elastic limit. So, it is defined as the stress developed in the material without any permanent set. So, the material will regain its original shape within this zone, the elastic limit. So, the material has elastic properties. So, here elastic properties, the material has elastic properties up to B, 0 to O to B, the elastic limit. Elastic limit. So, here if you load, stress increase, load increase, what will happen? Parallelly up to here, simultaneously, if stress increases, so strain also increase. So, similarly, so the stress, if stress at B up to B, the stress increases and strain also increases. So, it means O to B, there is no problem. Whenever remove the load, immediately regains its original shape. So, it means the material within the elastic limit. It means elasticity nature. So, beyond this point, one more point is there, that is C. This is upper yield point. Upper yield point. So, beyond this point, the material has started to yielding. So that is yield point. The material is stressed. Beyond point B, the plastic ray stays reach. So, on the removal of the load, so the material will not be able to recover its original size and shape. A little concentration will show that beyond point B, the strain increases at a faster rate with any increase in the stress until the point C is reached. So, here, see, up to B, there is no problem. The stress beyond the B, on the removal of the load, the material will not be able to recover its original shape and size. Why? Because it occupied the yield position, the deformation. It occupied plasticity nature. The strain increases at a faster rate with increase in the stress, so until the point C reach. See, at upper yield point. So, after behind this C point, so one more point is there. So, at this point, the material yields before the load and there is an appreciable strain without any increase in stress. So, in case of mild steel, it will be seen that a small load drops to D. So, immediately after yielding commences, what will happen is there are two yield points, one is C and D. The C and D are called as upper and lower yield points. So, the stress corresponding to yield point is known as yield point stress. So, this stress is called as yield point stress. See, up to here, this elastic property proportional limit stress, and then here also elastic stress, and then is at C point, this is at C yield point, upper yield point yield stress. At D, lower yield stress. C is upper yield stress, and D is lower yield stress. And then it keep on increases the load, what will happen? It reaches to maximum stress. This is ultimate stress. Maximum stress or ultimate stress. Ultimate stress. Clear? See, in this, the points C and D are called as upper and lower yield point. The stress corresponding to yield point is known as the yield point stress. Upper yield point stress and lower yield point stress. At D, the specimen regains some strength and higher values of stresses are required for higher strains than those between A and D. The stress or load goes on increasing till the point E is reached. So the gradual increase in the strain or length of the specimen is followed with the uniform reduction of its cross-sectional area. The work done during stretching the specimen is transformed largely into heat and the specimen becomes hot. The ultimate stress, that point is called as maximum limit or maximum stress or ultimate stress. So that point is E. So the work done during stretching the specimen is transformed largely into heat and then specimen becomes hot at E. Heat or it becomes hot. At E, the stress which attains its maximum value known as ultimate stress. So it is defined as the largest stress obtained by dividing the largest value of the load reached in a test to the original cross-sectional area of the test phase. So the maximum value reached. So the maximum largest stress obtained, the ultimate stress. Ultimate stress is equal to the largest value of the load. Maximum load upon cross-sectional area. Cross-sectional area. It gives the ultimate stress value, sigma u. So breaking stress. After the specimen has reached the ultimate stress, a neck is formed. So which decreases the cross-sectional area of the specimen. What do you mean by neck? So this applied specimen, so after keep on increasing the load, a neck formation will be possible. This is neck formation. D will be decreased and length will be increased. So little consideration will show that stress or load necessary to break away the specimen is less than the maximum stress. The stress is therefore reduced until the specimen breaks away at point F. The stress corresponding to point F is known as breaking stress. So at which the component will fail at this neck after formation of the neck. Why? Because already it has reached the ultimate stress. So which decreases the cross-sectional area of the specimen. So at this point the stress is called as breaking stress. In this diagram you can see This point is breaking stress or failure stress. So ultimate stress you can calculate by dividing the maximum load of the load reached in a test to the original cross section of area of this test phase. And breaking stress at which the component will fail. It breaks it. So after reaching the neck formation. The percentage reduction in area. So it is the difference between the original cross-section area and the cross-section area at the neck where the fracture takes place. This difference is expressed as percentage of the original cross-sectional area. So difference between the original cross-sectional area and cross-sectional area at the neck. Let A is original cross-sectional area and small is cross-sectional area at the neck. Then the reduction in area is A minus A. So and the percentage reduction in area is A minus the reduction in area is the original cross-sectional area minus cross-sectional area at the neck upon original cross-sectional area. So multiply with 100, it will get the percentage reduction in area. So A minus A by A into 100. Similar percentage elongation. So it is the percentage increase in the standard gauge length, that is original length, obtained by measuring the fractured specimen after bringing the broken parts together. Let gauge length or original length L and capital L is length of specimen after fracture or final length. Elongation L minus L. The percentage elongation is L minus L by original length, that is gauge length or original length multiply with 100. You will get the percentage elongation. So the measuring the fracture specimen after bringing the broken parts together. So next, so these 7 points are very important related to this stress strain diagram. So once again, see what are the important points in a stress strain diagram. Up to now we have learned. So in stress strain diagram, professional limit O to A is a straight line, and here it holds Hooke's law, an elastic limit up to the point B, and material has elastic properties up to the point B. This point is known as elastic limit. It is defined as the stress developed in the material without any permanent set. Yield point, upper yield point C and lower yield point D. C and D. The points C and D are called as upper and lower yield points respectively. The corresponding to yield point is known as yield point stress. Upper yield point or how do you calculate the yield point stress? Sigma y, E, y is equal to yield stress is equal to yield load divided by area. So similarly, ultimate stress at D, the specimen regains some strength and higher values of stresses are required for higher strains. when compared to A and D. So the work done at E, the stress which attains its maximum value is known as ultimate stress, the maximum load upon cross-sectional area. The breaking stress. So after neck formation, which decreases the cross-sectional area of the specimen, we keep on increasing the load, the material will fail. The stress corresponding to that point F is known as breaking stress. So now percentage reduction in area and percentage elongation you can calculate. So now we will discuss the working stress. So when designing machine parts, it's desirable to keep the stress lower than the maximum or ultimate stress at which failure of the material takes place. So this stress is known as the working stress or design stress or actual stress. It is also known as safe or allowable stress or permissible stress also. So always it is desirable to keep the stress lower than the maximum or ultimate stress. So already we have seen in stress strain diagram. Whenever reached the material to the ultimate stress, beyond this stress the component will fail. So that's why already we applied always the working stress less than the ultimate stress. So in stress strain diagram, we have learned O to A proportional limit and B elastic limit and C B to A to B or B to C upper yield point and C to D lower yield point and D to E ultimate stress and E to F is breaking stress. So all these points are very important in stress strain diagram. So now we'll discuss about factor of safety. So it is defined in general as the ratio of the maximum stress to the working stress. So mathematically the factor of safety is equal to maximum stress upon working or design stress. Working or design are allowable or permissible. All terms are same. In case of ductile materials, the mild steel example, where the yield point is clearly defined, the factor of safety is based upon the yield point stress. So that is yield point stress upon working or design stress. So the factor of safety you can represent the FOS, you can write like this. So maximum stress max by the working stress. So always the working stress is less than the maximum stress. So the maximum stress means the component, the material can withstand up to this stress value. So always the applied or working or design or allowable stress is less than this maximum stress for safe design. The factor of safety, that's why you should take proper value for proper application to avoid the failure. For safe design, the factor of safety is very important in designing. So in case of ductile materials, yield stress, and in case of brittle materials, cast iron, the yield point is not well defined as for ductile materials. So therefore, the factor of safety for brittle material is based on ultimate stress. So the factor of safety is ultimate stress upon working or design stress. Suppose here example, the maximum stress is 40 kilonewtons. So the working stress or design stress is 10 kilonewton. So what is the factor of safety? 40 upon by 10. So 4. Your factor of safety is 4. So suppose you have taken sigma max is equal to 40 and the working stress is 40 or 50. Sorry, here megapascal, not in newtons. So, what is the factor of safety here? 40 by 50, 0.2, 0.8. So, very less than the 1, this value, but it is not a safe design. Why? Because the factor of safety always should greater than the 1. So, remember while designing the component. So how do you select the factor of safety? The selection of proper factor of safety to be used in designing any machine component depends upon a number of considerations, such as the material and the mode of manufacture, type of stress, general service conditions, and the shape of the parts. Before selecting a proper factor of safety, a design engineer should consider the following points. The selection of factor of safety is very important. The proper factor of safety to be used in designing of machine components. The factor of safety depends upon the material. Which type of operation is required? That is a mode of manufacture. Which type of load applied? It may be tensile or a compressor or shear. That is a type of stress. The general service conditions and the shape of the parts depends upon these affecting the factor of safety. So design engineer should consider all these points. What are they? The first one is reliability of the properties of the material and the change of these properties during service. So reliability of test results and accuracy of application of these results to actual machine parts. So the reliability of applied load. So what is the reliability of applied load? Whether it is suitable or not, whether the material will stand or not. So based on this load and the application, depends upon the type of application and then the proper reliability of the properties, the selection of factor of safety depends. So the reliability of applied load, the certainty as to exact mode of failure. What are the failure conditions? What are the failure criteria? You should know before selection of factor of safety. So the extent of simplifying assumptions. If any assumptions made, you can extract of simplifying assumptions. The extent of localized stresses and then extent of loss of life if failure occurs. Suppose if failure occurs, so what is the loss? Extent of loss of life, the component life or product life. It depends upon the selection of factor of safety. So the extent of loss of property if failure occurs. Failure occurs, the extent of loss of property is a main factor, the deciding factor for selection of factor of safety. So that's why in a mechanical components design, so design engineer select one factor of safety before designing. So while designing or while selecting the factor of safety, the design engineer should remember all these points. So otherwise the component will fail. If not selected factor of safety, suppose in example I told you, suppose he has taken less than 1. So the maximum capacity, so load is the maximum, suppose the maximum load. So the maximum load is 50 kilonewtons. The working load, so the working load or design load is 60. But it is wrong. For safe design, to avoid failures or to minimize the cost, to improve the performance of the component, to improve the life of the component, you should select always good factor of safety. So here in this case, the working load, the working is load is 10 kilonewtons or 20 kilonewtons. So then the factor of safety you can calculate very easily. So 5. So the 5 factor of safety you have taken. So here never failures. Always in a safe design only. So that's why the factor of safety is depends upon the material and then the mode of manufacture process, which type of manufacturing process required for particular designing. It may be machining or drilling or grinding, and then type of stress and general service conditions and the shape of the parts. Which shape is suitable, reliable. You should design. You should define clearly. So before selecting a factor of safety, the proper factor of safety, you should remember all these points. Then your designed component will be success without fail. So for these topics, stress strain curve and elasticity and plasticity and factor of safety or working stress have taken references. S. Ramamurthy. The book title is Strength of Material. And R.K. Rajput, the Strength of Material title and H.M. Publications. And R.K. Bansal, a textbook of Strength of Materials. And R.S. Kurmi and Gupta, Strength of Materials textbook, H.M. and co-publications. So these textbooks are have referred for this PPT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.